Let's look at another example of a chi-square test on two variables. So in registering for a class, you probably want to know the grade distribution. But do you expect or want an even distribution? And you probably don't, and there's some reasons for that. And we'd probably expect with grade inflation, maybe there's more A's than there are D's, but we could test and see. But what's the bigger concern? The distribution itself probably is less important than its comparison. That is, you might care more about taking a class from a professor that has a grade distribution you like compared to your distribution of a different professor. But if there's nothing to compare to, you don't really have a choice. So how can we compare these two professors that teach this class? So one way would be to take their grades that they've given out in the past, so Professor Alpha and Professor Beta, look at how many A's, B's, and C's they've each given out, and then we're going to lump the D's and F's in together. Now the reason we're lumping D's and F's in together is that you should remember, with a chi-square test, we always need to have an expected value, or an expected count of at least 5 in any test that we're running. So in this case, if we don't lump the D's and the F's together, and the F's are a bit smaller, they'll be lower than 5 for our expected, and we can get a little bit funny results. So we take a sum of this, and we see that 69 students have taken Professor Alpha's class, and 33 students have taken Professor Beta's class. So we can look at the distribution. We see again that there's a fair bit of difference between these two distributions when we just look at the raw proportions of each. So here 16% of Professor Alpha's students have gotten A's, while 30% of Professor Beta's have. However, we also note that 14% of Professor Alpha's students have gotten D's or F's, while 30% of Professor Beta's have. So we want to use the chi-square test, but we're going to use the same tweaks we used before. So we first need to figure out that expected. So we find the row or column percents, just like we did in our previous example. So here we have the row percents, so 21% of the students all together got A's, 31% got B's, 28% C's, and 20% D's or F's. We then multiply the column, or row totals, so we take 69 alpha students times 21%, or times 0.21, we can get an expected number of students that would have gotten A's in that class. So we do all of that multiplication, and we show that we expect 14 A's in Professor Alpha's class and 6.7 A's in Professor Beta's class. We can then go ahead and find the differences. That's what we're going to do with to actually use the chi-square statistic. So we have our observes, we have our expecteds, and now we can use the formula to calculate the test statistic. And again, because we're going to be doing this in StatCrunch momentarily, I'm not going to make you calculate all 8 of these categories. So here we now sum up those differences. So note the sum of the observed minus expected squares divided by expected. We get a chi-square statistic of 8.489. So if we plug that into StatCrunch, which I'm not going to do at the moment because we'll show you how to do all of that in one fell swoop in a moment, we get a p-value of 0.0369. This means we reject the null hypothesis of no association between grade distribution and faculty member or professor. However, that tells us that there is a difference, but it doesn't tell us what that difference is. So we often want to look at the differences and residuals, which are just the standardized differences. So we want to see where the biggest differences are. So if we look back at this table of differences, so these are the contributions between, or from each of these values to the chi-square statistic, we see that Professor Alpha gives more or fewer A's than expected by chance, and Professor Beta gives more A's than expected by chance. In the middle, we see Professor Alpha gives more B's and C's, but down here we see that Professor Alpha gives fewer D's and F's. So your exact decision about what course you might want to take is probably going to be affected by whether you think you are likely to fall in this middle or on the outside edges of the distribution. That's a very important point to keep in mind whenever interpreting a chi-square test. Now that interpretation can also be a little bit tricky because it does not tell us causation unless you're analyzing an experiment. So unless we randomly assign students to those classes, we cannot say that Professor Alpha or Beta causes those different grades. In our example, there's a few possible interpretations. It could be that Professor Alpha is aiming for a more central distribution. Okay? He or she may want to give out more B's and C's. Or it's possible that really good and really bad students take Professor Beta's classes. So for some reason, maybe those students are drawn into Professor Beta's class instead of Professor Alpha's class. It's also possible they simply teach in different semesters. If Alpha were to teach this class in the spring and Beta in the fall, maybe there's a different type of students taking the course. This is especially important when we think about the fact there are two possible directions in the interpretation here. In the first example, we're saying Professor Alpha is the one causing this difference. In the second example here, we're saying that it's the students that are causing the difference between Professor Alpha and Beta's classes. It depends on how we interpret that or read that, whether we're testing for homogeneity or independence. Now, I'm going to be very clear here. I will not ask you a question on the quiz or the test to separate between these two ideas. However, the book says a lot about it, so I want to make sure it's made clear here. Independence simply asks if two randomly observed variables are independent. So if we went around campus and surveyed all students and got back their professor and their grade, we'd have a test of independence. However, if we had a test of homogeneity, we would be seeking out groups and then asking if those groups differed. So we would specifically seek out alpha and beta students or assign them into different classes if we were doing an experiment. And we would ask if that, or we would focus on the fact that that group is what causes the difference. The mechanics are exactly the same, but we have a slightly different interpretation. With homogeneity, we assume that the group we target, in this example, the professor, is the group that matters.